So what's the relevance of the test function if you can pick like any one?
Yeah, it's a good question. The relevance of the test function is that is exactly I can pick anyone. So remember, like the differential equation is actually an infinite dimensional equation in some sense, right? This equal to 0, not just for one particular x, but for all x's. So in this sense, it's actually not just the one equation, it's infinitely many equations, right? It's one equation for every x.
Mm-hmm.
But now coming to here, at the end, I got just the one equation. It's integrated, right? There is no longer any, I mean, this equation doesn't, it doesn't depend on where I choose x. I mean, it's actually integrated over x. So it's only one equation. So it's actually impossible to basically derive an equivalent equation. That's only one equation from an infinite dimensional equation, right? So the trick here is that the weak form is also an infinite dimensional equation in the sense that it has to hold not for any x as in the strong form, but for any v. It has to hold for any v that satisfies the boundary condition. You can choose a v that is like that. Okay, this equation has to be true. If you choose another v that is like that, this equation also has to be true. You can choose any v as long as it is differentiable. This weak form has to be true. Okay, so that's actually what constrains the solution u. So basically, u has to be this function that satisfies this equation for any v. Does it make any sense? Right. So again, going from the three different methods, the three different ways to look at the differential equation. In finite difference, the differential equation is the original differential equation, and we enforce it to be correct at a bunch of different data points, right? In reality, it has to hold for any x, even on the either on the grid point or not on the grid point. We just enforce it on the grid points. In finite volume, we perform the integral of the equation, and the integral form of the equation should hold for any domain, right? Any L and any R. We enforce it from the interval L to R. In reality, we enforce it for a finite number of volumes, right? From I delta x to I plus 1 delta x. Now, when we get to finite elements, we derive the weak form, and the weak form is supposed to hold for any possible differentiable v. And as you're going to see later on, I'm not going to be enforcing this weak form for any possible v. I'm only going to enforce this equality for a finite set of v's. Okay, so that's kind of how we are going to do next, derive the finite elements. All right, does that help? Any other questions? Okay, so I assume we are okay with this weak form, and then we're going to describe how we are actually going to discretize the weak form. All right. Okay, so how do we derive a linear system from the weak form? So let me again write down the weak form. Integration from 0 to 1, dv dx times du dx times dx equal to integration from 0 to 1 v times f dx. Okay, again, we are choosing, we want to find the solution u such that this weak form is satisfied for any v which satisfies the boundary condition v0 equal to v1 equal to 0. Okay, this is for any v that satisfies v0 equal to v1 equal to 0. Okay, this symbol means for any. All right, so the finite element says that two things. One is that we are not going to be looking at any solution u here. We are not choosing this from all possible function u's. We want to choose a U that satisfies a simplifying constraints. Okay, so for example, in the last lecture, what kind of simplifying constraints did we set? Remember? How did we approximate a function in finite elements?
It was piecewise linear.
Yes. For example, piecewise linear. And for example, and continuous, right? Okay. Particularly this kind of a simplifying constraint put the function u in a very convenient form, okay, that allows representation of u as linear combinations of what we call basis functions.